Okay, so we're going to take a look at determining the rate of a chemical reaction, which means calculating how fast we produce product or sometimes consume reactant, depending. And here it says they want to know the average velocity, which would be the rate of a car over the entire time period. They want it in kilometers per minute. I've got a data table. I've got kilometers here, minutes here. If they want it over the entire time period, then you would be looking at the first and the last data point. Agreed? Okay. So kilometers per minute means we're going to take the last point, so 125, and then minus 0 over 100 minus 0, right? So you're going to get 125 divided by 100, which will come out to be 1.25 kilometers per minute. So really, we just calculated the slope, right? So if they want to convert this over to kilometers per hour, then that means that you would need to convert minutes into hours, doing a basic unit conversion. And there are 60 minutes in an hour that will allow you to cancel minutes. And then that will give you 75 kilometers per hour. Okay, so since we're talking about the average rate or the average velocity here, it's not changing exactly the same between each time increment that they have listed in the data table. So we're simply looking at it between the first and the last point. And then generally speaking, a unit of what is always in the denominator when you're calculating rate? Time. Okay. So let's take a look at measuring the rate of a reaction. So underneath this section, we're talking about chemical kinetics. So kinetics is where we take a look at how quickly chemical reactions occur, and then what factors are going to influence how quickly it happens over time. Now, if you've got a firecracker exploding, that has a really fast reaction rate. The time for that reaction is less than a second. If you're trying to metabolize whatever you ate for lunch, that would take several hours, and then rusting a bicycle takes weeks to months. So that's a very long reaction rate. You can either look at the disappearance of a reactant or appearance of a product over time. And deciding what you're going to measure depends upon what states of matter do you have present, what do you have in the lab that you could use to measure it with. Let's take a look at the top of the next page. You also need to consider, okay, what units are we going to be using to represent the reaction rate? Generally speaking, you can use this equation to measure the rate of a reaction. You're going to measure the quantity of a chemical that's changing over time. Maybe you're measuring the volume of gas produced or pressure produced or the rate of pH changing. It really just sort of depends. But the one thing that you need to know is it doesn't matter whether you're measuring a reactant being consumed or product being produced. We generally report the rate of a reaction as a positive value. So we always take the absolute value. Even if it's a negative value, you would make it positive. Okay. Down here, they've given us an example of the consumption of something called thionyl chloride, and they gave us a bunch of data. If you were to plot this data, I'm not going to take a bunch of time doing it, but if you were to plot this data, you would get a graph that looks something like this over time. And so this is the consumption of thionyl chloride over time, and the consumption occurs the fastest at the beginning of the reaction because that's when the slope of the tangent line would be the steepest, okay? And then that tangent line slope would slowly be leveling off and decreasing over time. So once you get to the point where the reaction is almost over, your slope is really not changing much at all, okay? Let's take a look at the next page. Let's talk about the different ways to measure the rate of a reaction. So we've got various methods that we can use. Here we have a manometer. Manometers are used to measure the pressure of a gas formed during a chemical reaction. So you would have a reaction taking place inside a sealed container. The gas that is produced would be measured in certain increments of time. And then you've also got something called a eudometer. This measures the volume of gas produced during a chemical reaction. You've got an airtight container with the reaction in it releasing the volume of gas. You collect that volume of gas above water in something that looks like a burette, but it's really a eudometer tube because it has a closed end on it. Other things that you could use are, you can use an open container and a balance. So if you have a gas that's leaving an open system, an example of this would be if you've got a beaker without a lid. You can put that beaker directly on a scale. The mass will change over time because you're going to be losing gas to the surroundings, and you can simply measure it in certain increments of time by looking at the grams that are changing. Okay? All right, let's take a look at, I should probably write some unit examples in here for you just so you have it, okay? Since manometers are using pressure as the measurement, I would have something like a pressure unit over time, like seconds. Here's an example. Over here, you've got the volume of gas being changed, so maybe you're measuring this in milliliters per minute. And then over here, when you're balanced, this would be grams per minute or grams per second, whichever you guys decide. And then, did we miss anything here? We missed the concentration here. You can measure the change in concentration of something in a solution by taking a small amount out and titrating it at that instant moment in time. So that means you would be taking a look at molarity, over time for your units. And I think that's about it. You may sometimes hear them refer to titrations as titrimetry. Same thing. Let's take a look at the top of the next page. If you've got something in solution and that solution has got a distinct color, like maybe you are producing some ions in solution, like transition metal ions, you could measure the change in color over time. We actually have a device that we could do that with, like a colorimeter maybe. You can also measure the pH change over time. And let's see what else. Down here it says, if you have a color change, that's when we use a colorimeter. We can also use something called a spectrophotometer, okay? And I think that's all that we need to talk about there, okay? Did they put anything on conductivity in here? If you have a bunch of ions present that conduct, maybe the ions will appear or maybe they will be consumed. You could take a look at conductivity and you could measure that as well. Okay, let's take a look at a sample problem. The sample problem says, state 5 different methods for measuring the rate of a reaction of an iron nail in hydrochloric acid. So remember when we put an iron nail in something and you watched it change colors over time. It was a single replacement reaction. So here's what I would pay attention to. You've got a strong acid. As you consume that strong acid over time, what will change? What are a couple of things that you could measure?
Color, the mass.
It's colorless. pH. You're forming iron 2 chloride. Iron 2 is a transition metal. Transition metals tend to have distinct colors when they're in solution, okay? So since this says that we have a yellow-orange color similar to rust, that color is coming from this iron 2 ion that is in the solution, okay? So you could use a colorimeter or a spectrophotometer to measure the change in color over time, okay? Something else that you could do is you've got a gas right here. You're producing gas. What could you measure? Two things. Pressure and what else? Yeah, pressure and volume of the gas. If you had this reaction taking place in an open container and you had it on a scale, you could measure the change in mass over time because you would lose hydrogen gas to the environment, so the mass would steadily decrease over time. So here it says you could use a balance. Okay? You could determine the mass of the iron nail before and after the reaction. However, I think it would be a lot easier to simply measure the mass lost as the gas leaves. Okay, now, they've outlined a few things for you down here. Could have measured the change in concentration of the acid over time with a titration. We mentioned change in pH over time. We would use a pH meter. We also mentioned the change in the volume of the hydrogen gas over time. You would use a udometer to do that. The change in pressure of the hydrogen gas over time with a manometer. Or the change in mass as the hydrogen gas leaves, you'd have to do that on a balance. It would have to be an open container, okay? Okay, let's turn the page. Okay, let's take a look at some of these where we're indicating two methods for measuring the rate of the following reactions. Okay, in A, they mentioned that we have copper 2 ions. Those are transition metal ions. They're blue. So what could I do here? I could measure what? Yep, you could measure the color change. Okay, you would use a colorimeter or a spectrophotometer to make that happen. Let's take a look at B. What could I measure in B?
Pressure.
Yeah, you are producing two gases on the product side. So I would measure the change in pressure, or you could measure the change in what?
Volume.
Yep, the change in volume. Obviously, the volume is going to increase over time. How about C?
Also pressure.
I'm producing a gas. I didn't have a gas to begin with. So yeah, you could measure the change in pressure, the change in volume, and you could also measure the change in mass if you did this in an open container, okay? For D, I've got sulfuric acid and barium hydroxide. Yeah, you could measure the change in pH over time. You could measure the change in concentration of sulfuric acid by doing a titration at certain instances over time. You can measure the change in barium hydroxide concentration as well. You can't, however, measure the volume of water that is being produced over time. Like, there is no method that you have to make that happen. Does that make sense? Let's take a look at calculating reaction rate. Let's come down here. I need to stop this.